combinatorics in distinguishable objects. When we solve a permutation or a combination problem, the objects are distinct. There are applications that some objects are not distinguishable, and we want to know how many distinguishable permutations or combinations can be obtained. Let's look at this example. In how many distinguishable ways can the letters in the word statistics be arranged? But this question can also be asked as how many different words can be made by rearranging the letters in the word statistics, although many are not meaningful. So to see this one, and here we have 10 letters. We have 10 letters. So if we rearrange these 10 letters, that will be permutation 10 taken 10 a time. So this will be 10 factorial. But however, we know by rearranging them, some words, like some letters, like S, when you move them and we do not get new letters. So we need to exclude those by rearranging S or rearranging T or rearranging I. So then we need to know how many, letters by rearranging S, T, or I that we do not get new words. So, but we have 3S. So if you rearrange 3, that will give you 3 factorial, which is 1 times 2 times 3, that's 6. So there will be 6 ways. That does not give us new words. So if you consider similarly how we find combinations, then 10 factorial, this is the permutations we would get by rearranging 10 letters. But then 3S's that will have 3 ways that do not generate new letters. So we need to take a division divided by 3 factorial. We also have 3 letters, 3 T's, and that will be 3 factorial as well. So we need to divide by this 3 factorial because this does not give us new words. And then we have 2 I's, so that will be 2 factorial. So that divided by 2. Therefore, this will be the number of distinguishable permutations. And that, if you calculate, it should be 50,040. So these are the distinguishable permutations. In other words, these are different words by rearrange letters in statistics. From this example, we can generalize it or abstract it to a more general case. Theorem: distinguishable permutations. A collection of n objects has n sub 1 of one kind of objects, n sub 2 of a second kind of objects, n sub 3 of third kind, n sub k of a kth kind, with n sub 1 plus n sub 2 plus n sub 3 plus up to n sub k equals n. Then the number of distinguishable permutations of n objects is n factorial divided by these. And you can see this is just a direct generalization from the previous example like we had for statistics. And let's look at another example. Example 2. A variety pack of 18 snack-sized bags of potato chips contains 6 plain, 5 barbecue, 4 sour cream and onion, and 3 salt and vinegar bags. How many distinguishable ways may these bags be distributed to 18 kids in a party that each gets a bag? So to solve this question, and we may denote the 18 bags in terms of the flavors. So we have 6 plain chips. So we put P, 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 P. So that would be 6. And then we have 5 barbecue. So we use B for barbecue. B, 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 B. That's 5 bags. And then we have 4 sour and cream. So let's use S for sour and cream. So that would be 4. And then finally we have 3 salt and vinegar. Let's use V's to stand for that. So we have 3. So these are much like 18 letters we had in the previous example. So here we have 18 bags. And then we have these 6 same flavor, and this 5, this is 4, and this 3. So this would be 18 factorial, and then divided by 6 factorial, 5 factorial, 4 factorial, and 3 factorial correspondingly for these repeating flavors. So when we calculate this, we will get a large number. So this is 514,594,080 distinguishable ways to dispute these 18 bags. For homework, please see assignment number 39. Thank you.